Mastering dynamic programming through real-world problem-solving. Dynamic programming is not just another algorithmic technique. It's a powerful problem-solving strategy that transforms complex problems into manageable subproblems. By storing intermediate results through memoization or tabulation, developers can optimize solutions significantly. This approach is essential for tackling challenges ranging from optimization tasks to sequence alignment. The key insight behind dynamic programming lies in recognizing overlapping subproblems and optimal substructure properties within larger issues. When these characteristics are present, we can avoid redundant computations by reusing previously calculated values. This efficiency makes dynamic programming indispensable in competitive programming and software development scenarios alike. Fundamental principles behind dynamic programming. At its core, dynamic programming relies on two fundamental principles that guide effective implementation. Second, any given problem should exhibit optimal substructure, meaning an optimal solution contains optimal solutions to its subproblems. This duality allows us to break down seemingly impossible challenges into smaller components while ensuring each part contributes optimally towards the final result. For instance, when calculating Fibonacci numbers using traditional recursion, we end up recomputing values unnecessarily due to lack of memory storage mechanisms. By implementing either top-down approaches with memoization or bottom-up strategies via tabulation, we eliminate redundant computation cycles. Top-down methods use recursive calls with caching, whereas bottom-up builds solutions iteratively starting from base cases upwards. Memoization stores computed results in cache to prevent repeated calculations. Tabulation builds table iteratively solving subproblems in order. Both techniques achieve similar outcomes but differ in execution style. Memoization tends to be easier for initial implementations since it closely resembles natural recursive formulations. However, tabulation often provides better performance optimizations by pre-allocating data structures upfront. Distinguishing characteristics of DP solutions. Successful dynamic programming implementations share distinct features that set them apart from other algorithms. One notable trait is their ability to reduce exponential time complexity to polynomial levels by leveraging stored intermediate states. For example, consider the classic knapsack problem, which involves selecting items with maximum value without exceeding weight capacity. A naive recursive approach would explore every possible combination leading to O(2 to the power of n) time complexity. But with dynamic programming, we can solve it efficiently in O(n)W time, where n represents number of items and W is total weight limit. Another distinguishing factor is the structured way DP handles dependencies between subproblems. Unlike greedy algorithms that make locally optimal choices at each step, dynamic programming ensures global optimality through systematic exploration of all possibilities. This characteristic becomes crucial when dealing with problems requiring backtracking capabilities, such as finding longest common subsequences or shortest paths in graphs with non-negative weights. Core components of an effective DP implementation. An effective dynamic programming solution requires careful consideration of several critical elements. These include identifying suitable recurrence relations, determining appropriate state representation formats, and establishing correct initialization conditions. Recurrence relations define how to compute current state based on previous ones. Choosing the right relation determines both correctness and efficiency of the overall solution. State representations dictate how information will be stored and accessed during computation phases. Proper initialization ensures accurate calculation of boundary conditions before proceeding deeper into problem space. Missteps here can lead to incorrect results even if rest of implementation appears sound. Let's take matrix chain multiplication as case study. Here, our goal is find optimal parenthesization pattern, minimizing total number of scalar multiplications required for multiplying series of matrices. To model this problem effectively, we need to define dp I, j, representing minimum cost of multiplying matrices I through j inclusive. Then establish recurrence relation involving partition points k between I and j, dp I, j, equals min, dp I, k, plus dp, k plus 1, j, plus p, I1, asterisk p, k, asterisk p, j, for all k in I, j1. This formula encapsulates essence of dynamic programming by building upon smaller subproblems while considering all potential partitions for optimal outcome. Pitfalls and common mistakes in DP implementations. While dynamic programming offers significant advantages, practitioners frequently encounter pitfalls that hinder successful application of this technique. One common mistake involves misidentifying whether a particular problem actually exhibits necessary properties for dynamic programming applicability. Not all recursive problems benefit from memoization or tabulation techniques. It's crucial to verify presence of overlapping subproblems and optimal substructure before investing effort into creating DP-based solutions. Another frequent error occurs when defining recurrence relations incorrectly. Minor miscalculations in formulas can propagate errors across entire solution spaces, resulting in completely wrong answers despite appearing logically consistent initially. To illustrate this point, let's examine coin change problem variation where we want count number of ways making amount n with denominations d. If someone mistakenly defines recurrence as dp n plus equals dp nd, they might overlook different combinations arising from varying denomination orders. Correct formulation should instead involve considering each denomination separately while iterating through amounts systematically to ensure all permutations get counted appropriately. Advanced techniques enhancing DP performance beyond basic implementations. Advanced techniques further enhance dynamic programming effectiveness, particularly for handling large-scale problems efficiently. Space optimization strategies represent one such area, offering substantial benefits without compromising correctness. In many classical DP problems, full table construction isn't always necessary. Often, only latest few rows/columns are relevant for subsequent computations, allowing us to replace entire tables with optimized arrays, reducing memory footprint significantly. Consider the classic edit distance problem measuring minimal operations needed. Transform string x into y. Standard implementation uses O, mn, space where mn are lengths of input strings. However, since each row depends solely on previous row, we can implement it using just 2 rows, thereby cutting memory requirements in half. Similarly, in some applications like longest increasing subsequence, LIS, we don't need complete DP table but rather maintain auxiliary structures tracking necessary information for efficient reconstruction later. These optimizations become increasingly vital when dealing with constraints limiting available memory resources typical in modern computing environments, including embedded systems and mobile platforms. Case studies demonstrating practical applications. Real-world examples help solidify understanding of dynamic programming concepts beyond theoretical discussions. Let's analyze 3 practical domains where dynamic programming plays pivotal roles: bioinformatics, finance, and network routing. In bioinformatics, aligning DNA sequences remains central task, requiring comparison of genetic material between organisms. Dynamic programming enables efficient sequence alignment by comparing characters position by position while accounting for insertions/deletions via gap penalties. Financial institutions utilize dynamic programming for portfolio optimization tasks, maximizing returns under risk constraints. By modeling investment decisions recursively while incorporating historical market data patterns, analysts develop robust asset allocation models adaptable to changing economic landscapes. Network engineers apply dynamic programming principles in designing resilient communication networks capable of rerouting traffic dynamically amidst failures. Shortest path algorithms like Floyd-Warshall leverage DP techniques to pre-compute alternative routes, maintaining connectivity integrity even when primary links fail unexpectedly. Each domain demonstrates unique adaptations of core DP methodologies tailored specifically to address domain-specific requirements, showing versatility inherent in this computational paradigm. Evaluating time complexity trade-offs in DP algorithms. Understanding trade-offs between different DP approaches helps programmers select most suitable method for given scenario. While standard implementations offer predictable performance profiles, sometimes unconventional variations yield surprising improvements. Taking the classic Fibonacci sequence as reference point, simple recursion leads to exponential runtime due to repeated calculations. Introducing memoization reduces complexity, dramatically improving from O(2 to the power of n to linear O(n). Tabulation achieves same asymptotic bounds but may offer slight speedups depending on hardware specifics. However, for certain problems, specialized versions provide superior efficiencies. Consider the case of counting binary search trees with n nodes. Using Catalan numbers gives direct O(n) solution, avoiding explicit DP tables altogether through combinatorial mathematics. This illustrates the importance of exploring multiple avenues simultaneously when tackling challenging problems. Sometimes mathematical transformations reveal elegant shortcuts, bypassing need for elaborate DP frameworks entirely. Conversely, in situations demanding precise control over computation flow, custom DP architectures allow fine-grained adjustments, optimizing resource utilization according to specific needs of target application areas. Optimization strategies for large-scale DP problems. When dealing with large inputs, conventional DP approaches may struggle with scalability limitations. Fortunately, various optimization strategies enable handling massive datasets, effectively preserving accuracy while maintaining reasonable processing times. One prominent technique involves applying divide-and-conquer principles alongside DP paradigms. This hybrid methodology divides original problem into independent segments solvable individually before combining partial results intelligently. Asymptotically speaking, this approach can reduce time complexities substantially, especially for problems exhibiting special structural properties amenable to parallel processing. For instance, in segmented version of matrix chain multiplication, dividing sequence strategically minimizes overhead costs associated with cross-segment communications. Moreover, approximation algorithms serve as viable alternatives when exact solutions aren't strictly necessary. These probabilistic methods sacrifice absolute precision for dramatic gains in computational efficiency, useful in real-time decision support systems operating under strict latency constraints. Implementers must carefully weigh trade-offs between solution quality and performance metrics, ensuring chosen strategy meets project requirements without compromising functional objectives. Future directions and emerging trends in dynamic programming. Despite its long-standing presence in computer science literature, dynamic programming continues evolving, with new research directions opening exciting possibilities for future developments. Several emerging trends indicate promising trajectories shaping next-generation applications. Machine learning integration presents fascinating opportunities, enhancing traditional DP frameworks through intelligent heuristics. Reinforcement learning algorithms already demonstrate proficiency in mastering games like Go by evaluating vast decision trees efficiently, utilizing DP-like state transitions. Quantum computing introduces radical shifts, potentially revolutionizing DP landscape by enabling parallel evaluations of exponentially sized solution spaces simultaneously. Although still largely experimental, early prototypes suggest quantum-enhanced DP could tackle currently intractable problems within feasible timeframes. Additionally, advancements in hardware acceleration technologies promise improved runtimes for existing DP implementations. Specialized processors designed for tensor operations now show potential for accelerating complex DP workflows found in deep learning and scientific simulations. These innovations underscore enduring relevance of dynamic programming while highlighting its adaptability to technological progress, ensuring continued dominance in algorithm design discourse for years ahead. Conclusion: dynamic programming stands as cornerstone technique empowering programmers to solve intricate problems efficiently through strategic decomposition and reuse of intermediate results. Its principles have shaped generations of algorithm designers, influencing countless applications spanning diverse industries. From foundational theory to cutting-edge implementations, Mastery of dynamic programming demands persistent practice navigating varied problem domains, continuously refining analytical skills required for effective application of this versatile paradigm. The journey toward expertise begins with understanding core concepts, thoroughly followed by deliberate exposure to a wide array of problems, gradually increasing difficulty level, progressively honing technical abilities until confident tackling any challenge encountered professionally.